All of the work we've done so far has been in a two-dimensional coordinate system. Now I'm going to introduce the XYZ coordinate system. This is a three-dimensional system, and it will allow us to apply concepts of calculus to things that exist in three-dimensional space. In our previous work with trajectories, we used only positions that could be modeled by x and y coordinates. The position of a point in this system is specified by an ordered pair xy, where x specifies how far the point lies horizontally from the origin, and y specifies how far the point lies vertically from the origin. But all points in this system exist in a single xy plane. If, however, I'm interested in a point that lies above the xy plane but is still referenced at the same origin, I need to add a third coordinate to specify that point in space. The addition of this third coordinate now gives me an ordered triple, xyz, where x and y still represent the horizontal and vertical distance from the origin, but z specifies how far above or below the plane that the point will lie. The set of all points described by an ordered triple xyz is called three-dimensional space, xyz space, or it can be referenced as R3, where the symbol for the real numbers is used for R, and the 3 appears in the exponent space. The three-dimensional coordinate system is created simply by adding a third axis that we'll call z to the xy coordinate system we already have. This z-axis will be perpendicular to the x and y axis at the origin, and we call this system a three-dimensional rectangular coordinate system, or an XYZ coordinate system. We will also use similar sign conventions for this three-dimensional space, and we'll talk about that in a minute. This system can also be referred to as a right-handed coordinate system. If you can imagine placing the fingers of your right hand along the x-axis with the thumb extending in the direction of the z-axis, and then you curl your fingers inward toward your palm, your fingers will begin to point in the direction of the y-axis. The XYZ coordinate system is three-dimensional. We now have three intersecting planes: the xy plane, the xz plane, and the yz plane. These three planes divide XYZ space into 8 regions that we call octants. The point where all three planes intersect is called the origin, and it has coordinates 0, 0, 0. This representation has values of x in front of the origin that are positive, values of y to the right of the origin that are positive, and values of z above the origin that are positive. This means that in the right upper front octant, I have all three coordinates being positive. In the lower back left octant, all three coordinates are negative. In the upper right back octant, I have negative, positive, positive. In the upper left back octant, negative, negative, positive. In the upper front left octant, positive, negative, positive. In the lower front left octant, positive, negative, negative. In the lower front right octant, positive, positive, negative. And in the lower right back octant, negative, positive, negative. Let's work an example where we plot points in 3D space. I want to plot the following points in XYZ space. P has coordinates 3, 5, 4. Q has coordinates -5, 2, -4. R has coordinates 0, -4, and 3. For the point P, I first go out 3 in the positive x direction. Then I trace out 5 in the positive y direction and find the intersection point right here, and then from that point I go up 4 in the positive z direction, putting a point P with coordinates 3, 5, 4 above the xy plane. For the point Q, I need to add my negative x-axis and my negative z-axis because those two coordinates are negative. I go out -5 on the x-axis, go over to +2 on the y-axis, and below that intersection point I go down -4 in the negative z direction. This gives me a point below the xy plane that has coordinates -5, 2, -4. For the point R with coordinates 0, -4, 3, I don't have to move out in the x direction at all, but I do need to add the negative y axis. And I go out -4 along y, and up from that 3, and put my point with the coordinates 0, -4, 3. This point sits above the xy plane, and it is contained inside the yz plane. Now I want to move from lines to planes. Plotting points in the xy coordinate system with only two coordinates in my ordered pair will allow me to describe lines. The set of all points in the xy coordinate plane is also the set of all points in xyz space that have a z coordinate of 0. Plotting points in the xyz space allows me now to describe planes. Simple planes in xyz space can be described with equations like x is equal to 2, y is equal to -5, or z is equal to 17. In each case, the other two coordinates are completely arbitrary. Each of these equations describes a plane that is going to be parallel to one of the other planes. The plane x is equal to 2 will be parallel to the yz plane. Y is equal to -5 is parallel to the xz plane, and z is equal to 17 is parallel to the xy plane. Let's work another example. I want to determine the equation of the plane parallel to the xy plane that passes through the point 3, 2, -3. In order for the plane to be parallel to the xy plane and passing through the point 3, 2, -3, I need to look at the z coordinate of my ordered triple. The equation for our plane is going to be given by z is equal to -3 because the x and y coordinates are arbitrary. The plane that is parallel to the xy plane will be a plane defined by the z coordinate. We also can compute distances in xyz space. In the xy coordinate plane, we knew that the distance formula was given by d is equal to the square root of the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared. Let's see what might happen if I move this idea into xyz space. I'm going to plot 3 points in xyz space. P has coordinates x sub 1, y sub 1, z sub 1. Q has coordinates x sub 2, y sub 2, z sub 2. And R has coordinates x sub 2, y sub 2, z sub 1. The points P and Q both have the same z coordinate, so they are coplanar, and the length of the line segment, PR, will be given by the square root of the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared. Now this line segment is one side of a right triangle. The hypotenuse of this triangle is the length of the line segment PQ. So my line segment PQ is going to have a length given by the square root of the length of the line segment PR squared plus the length of the line segment RQ squared. And based on the work we did on the earlier slide, the square of the length of the line segment PR is given by the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared. And then I'm going to note that the length of the line segment RQ is given by z sub 2 minus z sub 1. And the square of the line segment RQ is given by z sub 2 minus z sub 1 quantity squared. So my line segment PQ has a length given by the square root of the quantity x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 squared plus the quantity z sub 2 minus z sub 1 squared. The distance between P and Q will be given by this expression. So let's work an example. I want to plot the points P specified by the coordinates -4, 3, -1, and the point Q specified by the coordinates 7, 5, 6, and then find the distance between them. I set up my three-dimensional coordinate system. I'm going to mark off the points on each axis that correspond to the coordinates I'm going to need. Now I'm going to go out -4 on the x-axis, out to 3 on the y-axis, and down to -1 on the z-axis. This puts point P at the coordinates -4, 3, -1. This point sets below the xy plane. Then I'm going to go out 7 on the x-axis, out to 5 on the y-axis, and up to 6 on the z-axis. This puts point Q at the coordinates 7, 5, 6. My distance between P and Q is specified by my formula. I'm going to plug in the values I have. The length of the line segment PQ is given by the square root of 7 minus a minus 4 quantity squared plus 5 minus 3 quantity squared plus 6 minus a minus 1 quantity squared. This becomes the square root of 121 plus 4 plus 49, which is equal to the square root of 174. I'll leave it like that because that's an exact value. So now you get to try it. Pause the video and plot the points P specified by the coordinates -2, 3, and 0, and Q specified by the coordinates 4, 1, -2. Then compute the distance between the 2 points. When you're ready, restart the video to check your understanding. The first thing I need to do is set up my coordinate system, and I'm going to plot the coordinates on the axes that I'm going to need to plot the first point. I go out -2 on the x-axis and out 3 on the y-axis. I have to go up 0 on the z-axis, so this point is contained entirely within the xy plane, and it's specified by the coordinates -2, 3, and 0. Now I'm going to go out 4 on the x-axis, 1 on the y-axis, and down -2 on the z-axis. This point sits below the xy plane, and it's specified by coordinates 4, 1, -2. The line segment PQ has a distance specified by the square root of -2 minus 4 quantity squared plus 3 minus 1 quantity squared plus 0 minus a minus 2 quantity squared. This simplifies to the square root of -6 squared plus 2 squared plus 2 squared. This reduces to 2 times the square root of 11, and this is in exact form. This is how we can expand everything that we've done in two-dimensional space into three-dimensional space by adding that third coordinate and that third axis. Be sure and let me know if you have any questions.